Perfect.
All right, yeah, you can go to the next slide. So yeah, well, I'm really glad to meet some college students that are actually ham radio operators. And tonight I want to talk about amateur radio astronomy and especially pulsar detection. And our group in Colorado, it's called the Deep Space Exploration Society, and almost all the members are ham radio operators because it takes a fairly good understanding of ham radio to take the jump into amateur radio astronomy. But I'll talk a little bit how we got this dish, and then some basics of radio astronomy, and then the bulk of the meeting will be on pulsars, what they are and how we detect them. So go to the next one. That's a picture of our dish out there. It's way out in the middle of nowhere in southeast Colorado. We're a nonprofit, and basically we're for amateur radio club. We do amateur radio astronomy, ham radio, and science, that kind of thing. We have a 60-foot telescope. It's near Haswell. It's called the Paul Plishner Radio Astronomy and Space Science Center. Our website is just dses.science. And if you want to email anybody, just information at dses.science. So go to the next one. Yeah, shoot, we're losing some text. Hopefully I can remember what these are about. So so when I'm done, I'll send you a version in PowerPoint that I think would be correct. But basically, the Air Force built, the Air Force had these two dishes in Boulder on the left. Those are two dishes in Boulder, 60-foot dishes, and a similar one down in Haswell. They were built in the 1950s for tropospheric studies, and the Air Force operated it for the National Bureau of Standards from 1958 to 1974, and then it sat idle after that. So the one on the right is the dish out in Haswell, and there to the right side of that dish is the trailer. That's an old 1960s style government trailer where we have our radios and receivers and racks and everything. So it's kind of cramped in there. And then there's that 60-foot dish that we have. Even though it was built a long time ago, they built it like a ship. It's just solid steel when you go in that pedestal. So go to the next one. These are the original specs on it. It's not a solid dish. It's actually, when you look at it closely, it's got a lot of little perforated holes in it. So it's got tiny holes in it. So that limits the frequency, but the operating frequency is basically 400 megahertz up to 2 gigahertz. And it is a 60-foot dish, parabolic. It's prime feed. And you can go to the next one. So just a little bit of the history. DSES started in Boulder in 1991, and their goal is to restore those two 60-foot dishes up there. And they got off to a good start. And then after 9/11 happened, Table Mountain was closed to amateur radio operators because Table Mountain is actually a federal government research site. So they closed it, couldn't get in there anymore. So then what they did, the Haswell site had been dormant from like 1974 to 2009, 30 some years, just sitting there. Paul Plishner was a radar contractor. He purchased it from the government at a government auction. He had some plans for it, but he never did anything with it. Eventually he donated it to DSES in Boulder. And in 2009, the group in Boulder started restoring the dish in Haswell. So they brought down the trailer, they stripped some gears and motors out of the dish at Boulder and brought it down, and they spent about a decade working on it, rebuilding the one in Haswell. The membership slowly transitioned from a lot of people in Boulder to a lot of people in the Springs, simply because it's too far to drive from Boulder. They would spend half a day driving from Boulder, and then they'd spend a weekend down there and wearing them out. So most of the members now are either in Colorado Springs, or we have quite a few remote members. a guy in Canada, a couple on the East Coast and West Coast, and they call into our Zoom meetings. But it's operational now, and it just like any ham operation, it's just a ton of volunteer hours got it going. So go to the next one. So just a little bit about radio astronomy. On the top is the spectrum. You see the color bars, that's where the optical frequency is. To the left of the optical, we have the gamma rays and X-rays, and our atmosphere is opaque to that, so the sensors are on satellites. And then to the right of the visible light is the infrared. Again, the sensors are mostly on satellites in space. But then up to the right, around between 10 centimeters and 10 meters is the atmospheric window, where the atmosphere is transparent to radio, and that's roughly between 5 megahertz and 30 gigahertz, and that's where we do a lot of the radio astronomy from the ground. The radio waves are much longer than optical waves, so a radio telescope must be a lot larger than an optical, because you're just doing based on the wavelength. And our goal is the same goal as it is in your ham shack. We want to minimize the RFI and maximize the signal to noise ratio. Next slide. So this shows the the strength of the radio signals we are tracking, and we measure the signals in something called the flux density. The units are Janskis, and the Jansky is defined as 10 to the minus 26th watts per square meter per hertz. So it's a tiny amount of energy per square meter at the frequency. Here in this chart, in the middle of it, we see where the supernova remnants can be detected at the various frequencies. The frequencies on the bottom and wavelengths up on top. So there's Cassiopeia A, Taurus A, Cygnus A, some of the supernova remnants. M31 is the Andromeda Galaxy. What I look for are pulsars. Pulsars are very weak, and they fall off the bottom of this chart. So they're in the millijansky region. They're down below one Jansky. So it's very weak signal. I got started in pulsars from doing weak signal propagation in ham radio. I was interested in like FT8 and Whisper, and getting signals around the world on half a watt, and then that helped get into this. So next slide. Some of the things we do with the 60-foot dish, we do have a ham station there at Haswell. It's a station, is the letters K0PRT is for the Plissner radio telescope. One of the main things we do is moon bounce, the Earth-Moon moon bounce at 1296 megahertz. And so we participate in the ARRL contest, mostly CW and digital. Digital's done with the WSJTX Q65 mode, because you have to count for the Doppler shift. There's a 2.5 second delay. When you send a signal to the moon, get it back, 2.5 second delay. So it makes voice a little bit harder. We also do 21 centimeter neutral hydrogen. So neutral hydrogen is the most abundant element in the universe, and neutral hydrogen, the electron will spontaneously transition. It does it. It's called the spin flip. They'll be spinning in the same direction, and then it'll spontaneously flip to the other direction. The average hydrogen atom in space will do that. It takes about 1 million years, so that's a long time. But there's vast quantities of hydrogen in interstellar space. So the space between stars is not empty vacuum. It's got a lot of neutral hydrogen floating around, especially anywhere near a supernova. There's lots of hydrogen clouds. So we can study the spectral lines from that, map the Milky Way. We can detect supernova remnants and things like that, radio galaxies. Then the other thing we do is detect pulsars. Pulsars are broadband emitters, and we look for those generally at 400 megahertz, or 1296, or 1420 are the three different feed horns we use. Next one. Before I get into the pulsars, I do want to talk about other projects that might be of interest. The first one I have there is SARA, is the Society of Amateur Radio Astronomers. So you can just go to their website, radioastronomy.org. If you're interested in radio astronomy, they have lots of helps to get started on various projects. And they're actually having a conference next week in Bishop, California. If it stops snowing out there. It's actually not in Bishop. Caltech runs a radio astronomy observatory out there in Owens Valley. So it's going to be there for a conference. Neutral hydrogen, you don't need the big dish that we have to detect it. You can do it with a small horn or even a 2 or 3 meter dish. And then I list some software there. The first one is West Virginia University has a project. And then the next one is GitHub. Virgo is another software package you can get on GitHub. And so these packages include GNU Radio. So most things we do are SDR based, and these packages already have GNU Radio set up. And so it doesn't take a whole lot to get going. There was another project here. I can't see the text. I'm sorry, it's chopped off, but so a couple other projects I want to mention was the radio Jupiter is you can actually detect the magnetic storms on Jupiter with an SDR at around 20 megahertz. They're in the HF, and that's an SDR. So now they're using an SDR play. Wideband like 16 to 24 megahertz, and you get very nice charts on that. Let's go to the next chart. So another project I want to mention is this 2-dish interferometer at Haswell. We have two 3.8 meter dishes. It's basically 12-foot dish. We have C-band feed horns for those. These are commercial broadcast dishes that are being discarded, and we're picking them up. They're solid dishes, so they'll work on a lot more frequencies than this. It's a student-led project, so there's two guys graduated EE from University of Washington last year, and they joined our group and were interested in the interferometer, so they're kind of leading the design of it. And we hope to get it all stood up this summer. And it's going to allow remote operations. We're going to put some linear actuators on the elevation control and have it remote controlled over internet. And if that's something you might be interested in, we welcome you to join, because this one, like I said, is completely remote. You'll be able to access it over internet, collect data, process it. It's going to be Raspberry Pi and SDR based, just a two-dish interferometer. So you won't learn a whole lot of the science like you do with a large array of interferometers, but you will learn how an interferometer works. We've also just stood up a remote ham station. It's HF plus 6 meter. And so we have several guys that live in Denver or live around that can't get down to Haswell a lot, but want to do ham radio. So we have this remote station that's operational now. We meet Zoom twice a month, the second and fourth Monday at 6:30 Mountain Time. Remote members are always welcome. If you want to join, just send us a note and we'll send you the link. Next slide. This is just a couple of the research things we've been doing. One is the pulsars. Once you detect it, then the interesting thing on a pulsar is look at the time of arrival for the pulse and compare the measured or the observed time of arrival with what's predicted by the models. And they don't agree. There's always a discrepancy, and that discrepancy lets you look for differences in the hydrogen clouds and pulsar characteristics and things like that. I've also looked, the second one is a fast folding algorithm. So I'll talk a little bit about this in a minute. You can detect pulsars either in time domain or in the frequency domain. We've done work with the solar eclipses. I think, Matthew, you said you guys have a GRAPE 1. We don't, but I think I put our name on the list. We'd like to get a grade 2 when they become available and just do the Doppler WWV monitoring during the eclipses. Next slide. All right, so yeah, and feel free to stop me anytime if you have a question. This is informal, so just if you have questions, speak up. That was just kind of a real quick overview. Now I'd like to get into pulsars, so we'll go to the next one. Pulsars are highly magnetized, rapidly rotating neutron star. You wonder, well, what's a neutron star? Neutron star is the collapsed core of a supernova explosion, the supernova remnant. And from our perspective, they appear to emit periodic short pulses of electromagnetic radiation. They're broadband emitters. Some of them go up into X-rays, gamma rays. The ones we're looking at are in the radio. There's basically two things we can observe. We see a pulse, so we can monitor the pulse and determine the spin period and the spin period derivative. So the spin period derivative is the rate of change of the spin, because they are losing energy as they emit the radiation and spin. So there's a spin down rate. Pulsars are very consistent with their timing. They're as consistent as atomic clocks. And so they've done a lot of studies on the accuracy of pulsars. The period of a pulse, some pulsars are down around a millisecond, 5 milliseconds. Other pulsars are over 1 second, maybe up to 10 seconds. So it varies. Originally, well, pulsars were first discovered in 1967. A gal in Britain was working on her PhD, and she did the work to discover the first one. And originally they had kind of a lighthouse model, basically like a magnetic dipole of the neutron star with the two ends of the magnetic pole sticking out north and south. And they kind of thought, well, that's what the model is. But just recently, NASA using this, it's called the NICER. It's a neutron star composition experiment. It's an X-ray sensor. It's actually on top of the International Space Station. And the purpose of NICER is to map the surface of nearby neutron stars. And so what I'm showing here is the first one. This is a simulation that NASA did to match the data they have. And surprisingly, what it shows is there's two sources of radiation emission, both in the southern hemisphere and nothing in the northern hemisphere. So this set everybody to scratching their head, wondering, these things are more complex than they first realized. Something else to think about is the X-ray emission is not always detected in phase with the radio emission. And what that means is they're not emitted at the same altitude in the magnetosphere. So the radio waves we get come from the magnetosphere, but we don't know how high above the surface, and evidently X-rays and radio waves can come from different points in that. So these are very intense magnetic storms that are poorly understood. The physics is still being worked on to understand it. Next one. This is called the PP dot diagram. So on the bottom is the spin period, and on the left is the period derivative. And these are logarithmic charts. But just from the period and period derivative, they can determine something called the characteristic age. The characteristic age is an indicator of age. It's not actually the true age. We don't know the true age, but it's an indicator of how old the neutron star might be. They can determine the minimum magnetic field strength that would be required to keep this thing going, and the spin down luminosity. What we'll be talking about a little bit later are the ones down in the lower left corner. These are binary pulsars. They call them recycled because it was two binary stars. One was larger, and one basically recycled the other one by accreting material from the companion star, and it became the larger, faster pulsar. These pulsars are older, and they're the most stable ones. They have a very narrow pulse, and they're very, very stable, and they're good for research. Next one. So there's two things when we're tracking pulsars that you have to worry about. And the first one is dispersion. These are broadband signals, and the higher frequencies are detected slightly earlier than the lower frequencies, and that's due to the pulse dispersion through all these free electrons in the interstellar medium. So the interstellar medium has got all these free electrons, including even our own solar wind from the sun, that cause the higher frequencies to get here a little bit earlier, and that smears out the pulse. And so what's shown on the right is the uncorrected pulse. And so we have to apply a little algorithm to correct that. And then once you've corrected that, then you can integrate a whole bunch of collections together to get an average pulse. And that's what's shown on top there is an indicator of the integrated profile. The dispersion measure itself is proportional to the density of electrons along the line of sight. But you can imagine if you're looking straight down the arm of the Milky Way towards the center of the galaxy, you're going to have a much higher density than if you're looking perpendicular up to something outside the Milky Way, where pretty quick you're just looking out in empty space. So the dispersion measure can indicate distance, but it kind of depends on the look direction. And then the second thing, go to the next chart. The second thing that we have to deal with is, like I showed earlier, these have very weak signals. So the top cartoon shows just some signal, looks like random signal. Well, there's actually a pulsar signal buried in there. And what we do is something called folding. If you know ahead of time what the period is, like say 1 millisecond, then you basically fold your data at 1 millisecond, and the bottom shows what the result of folding is. You're just kind of like folding a strip of paper, you're stacking it up, and you integrate these very small contributions until the pulse itself appears above the noise level. In our case, for amateurs, we're quite happy to find a known pulsar. We know ahead of time the direction it is, how far away it is, and we know the period very precisely from published data. If you're looking for a new pulsar, you have to do blind search. You collect the same data, but you search through it. You don't know the direction, the distance, or how fast it spins. So we kind of focus on just detecting known pulsars. The shape of an individual pulse can vary significantly, but the average pulse, so we average over thousands of these folds, we average over a large number of them. And if you compare the average pulse today with the average pulse yesterday, they're going to be very close, very, very similar. Next one. So this illustrates the actual detection process. On the left, you have the neutron star spinning around, emitting this radio beam. Then we have the telescope dish. So the dish itself is just collecting the waves. It's a prime focus parabolic dish. So the waves come in, they bounce up to the prime focus in the middle of the dish. That's actually where the antenna is. The antenna itself is something we put in the feed horn. So when we change feed horns, we're up there in the middle of that dish structure there, putting in either 400 megahertz or 1296 or 1420. And the antenna itself is just a simple little dipole antenna inside the feed horn. And then we run coax or hardline coax down to the receiver. The receiver, in our case, we're using, you can use a SDR, any SDR. We have a USRP B210. So we can run that up to 56 megahertz bandwidth, and it works pretty well. So then we collect the data. We have to kind of analyze the pulsar ahead of time, figure out how long do we collect data. So it's a batch process. We'll collect data for 10 minutes on a bright pulsar or 4 hours on a weak one. So it can be hours of data, gigabytes of data. And then after we collect the data, we can do the dedispersion and folding that I just talked about. And that basically brings out this mean pulse profile, the average pulse profile. And from that, we can calculate the time of arrival. and we're using GPS for our time reference. So that, in kind of a nutshell, is how we do it. We're going to talk more about the specifics here. So go to the next one. Nice thing about internet is the optical observatories have taken tons of digital surveys, and their data is all available for public consumption. Same thing with radio astronomy. There's lots and lots of data available, raw data, processed data, that's just available on the internet. Most of these large observatories are tax funded, and so we believe in open data. This is an example from PARCS, which is a 64-meter radio telescope in southern Australia. And B0833-45 is Vela. It's the brightest pulsar there is. And this is a time series snap. So along the top, you see it says 7.8, 7.9, and 8, roughly a tenth of a second between those pulses. And down at the bottom, I say that the period is 0.089 seconds. So it's very strong pulse. The pulses are way up above the noise floor. They're constant. So this is the best you would ever see. If we go to the next slide, this is what we usually see from Haswell. So this is a different pulsar, B0835-41. By the way, pulsar names are given by the right ascension and declination. So it's 0835 right ascension in hours and 41 degrees in declination, minus 41 degrees in declination. From where we are in Colorado, we can see down to about minus 44, minus 45. That's about the limit. The B on it means that it's referenced to 1950. Most of them are going to have a J name, and those are referenced to the Epic 2000. So this is what we normally see in Haswell. Down at the bottom, it says what the period should be. It's 0.75 seconds. So I look at this and I can't see with my eye that there's something in there every 3/4 of a second. There's just a lot of noise. So later on, I'll show what this pulsar looks like when we do the folding and the processing. Next chart. Here's an example of the Crab Nebula. It's a famous one. So this is the Crab supernova remnant, first observed in China in 1054. The Crab pulsar itself is the red star in the very center. There's only 2 or 3 pulsars that have an identified optical counterpart, because most pulsars are a neutron star, which is not glowing in the optical at all, and you just get the radio pulse. But this is a case where the optical and the radio are identified there. It has a period of 33 milliseconds, and this is a NASA image using Hubble data for optical in red and Chandra X-ray satellite telescope in blue. Next one. Oh, and by the way, Crab is one we have detected that at Haswell. Now we don't get a very nice image like that, but I'll show you later what we get. Amateurs have detected pulsars just using basic Earth, Moon, Earth equipment. Several people have used 3-meter dishes with the AirSpy SDR. A guy in Britain has used he's got a twin 23-element Yagi with the basic RTL SDRs. The requirement is you have to be able to track the pulsar. You have to have accurate pointing, and you have to be able to track for several hours and then integrate the data. The best hunting frequencies, and again, we change feed horns. The best for us is around 408 megahertz at 1296, and then again at 1420 megahertz. Next one. So this shows how we're configured. On the left, just say it's GPS clock sync. For the data processing, we use a 32-core Ubuntu 2204 host, and we use the B210 SDR that I mentioned. We have several different feed horns, and people that are interested in feed horn construction and experiments are welcome to build feed horns and try them. We use one at 408 megahertz, which is linear polarization, has a 30 dB low noise amplifier on it, and we use wideband filters on it. So it's 90 megahertz. And then we have a 1296 and 1420 feed horn, and those are both circular. On the right, so in order to plan, even, you figure out ahead of time, once and the first Pulsar DSES detected was in 2020. So we've only been doing this a couple of years. We have 24 of them so far, 24 unique pulsars that we've detected. And, it's pulsar detection is kind of like ham radio contest. People get involved in it. And so there's kind of loose running competitions to see who can collect the most. And there's a site in Germany that has a very nice telescope, and they've detected over 100 pulsars, and they've done some very advanced work there. So I use a software tool from an Italian ham operator. His call signal is I0NAA. He's got a tool called Murmur, which connects to the database that we all use from Australia to get the ephemeris data. And then you have to tell Murmur your location, your latitude and longitude and elevation, and the date when you're going to look, and then it'll use the data to figure out what pulsar might be visible. Now, pulsars can be tracked day or night. We just can't track near the sun. We stay 20 degrees away from the sun, but even if the sun is up, we can still detect a pulsar if it's away from the sun, because the sun is such a big radio noise source. So most of the time we go down there, we're spending all day detecting pulsars. Even though you can't see it visibly, the radio waves still come through the atmosphere fine. And we also use Stellarium. You might have seen Stellarium. It's a very popular app. It can run on your phone. It's like your own private planetarium. And then we use the database to get the ephemeris data. We have a team of 3 people that have developed some custom pointing and tracking software, because when they refurbished the dish, they, it had all these old analog control components, which are still in there as a backup, but they basically replaced the whole control string with a Linux laptop and a Raspberry Pi. So there's a Raspberry Pi up in the pedestal tower that controls the actuators. I think we have 12-bit encoders, and controls the motor. So that's all a custom pointing and tracking, and we get about 1/10 of a degree accuracy. We can track the moon 12 hours and stay right on all the time. So it's impressive that the whole thing still works, and it works well. So when we're doing pulsars, we have an old HP spectrum analyzer. I also use software spectrum analyzers, GNU Radio. First, we have to calibrate the gain on an SDR, get everything calibrated, and check for RFI. It's fairly quiet out there, radio. There's nothing nearby, but we do pick up stray signals coming out of air traffic control. There's all kinds of over the horizon radars and things like that. So it depends on the frequency. For the B210 SDR, we use GNU Radio. The GNU Radio does the analog to digital conversion and generates, it's a filter bank where the data is in the frequency domain in the filter bank. So that's our raw data. And then we use this Presto tool with Tempo. Tempo is the timing, and Presto is the pulsar detection tool. The Riptide tool is another pulsar detection tool that works in the time domain. And then there's some other utilities we use, but that's the basic setup. All of this is available. The software is all available free. The Presto is a professional tool, so there's some good instructions on installing it, but it's a workout to get it installed and running. And then there's some tutorials, but it's the same package that they use at professional sites, because as amateurs, if we come along and say, oh, we detected this pulsar, well, somebody's going to say, prove it. And so we can pull up these Presto plots. And so go to the next chart. This is what a Presto plot looks like. B0329 plus 54 is the brightest pulsar in the northern hemisphere. And it's every time we go to Haswell, it's the first one we check just to make sure everything's working. We calibrate against it. And it produces this plot. So on the left, on the top, we want to see a strong folded pulse. And so the noise level is real low on this. We have a very strong pulse, and it's showing 2 phases of the pulse. So it's 2 complete phases of the pulse. The chart on the below that on the left is a time phase plot. So phase runs along the bottom for 2 complete phases. Time goes from 0 up on the left. In this case, it was 600 seconds. So it's a 10-minute collection. And what you see right in the middle, lining up with the phase of the pulse on top, is you see that black line through the phase plot. So, and there's another one over next to the edge. Both of those need to line up in phase with what you see on top, and you want to be able to distinguish it. So that shows up real good. Then the at the bottom of on the left, it says the signal to noise ratio increases with observation time. So again, time starts on the bottom and goes up. And what this is showing is your SNR is increasing. They actually use something called a reduced chi-squared method, but it's equivalent to the SNR, which is easier to understand. So we always look for that to be increasing. Now over on the right, the arrow points to the middle chart. The middle chart is a frequency phase plot. Again, it's 2 entire phases on the bottom. Along the vertical axis is the frequency. So in this case, I was going from 415 to 435 megahertz. So this was taken just last year, and we were using a 408 megahertz feed horn. Oh, actually antenna. I guess below 1 gigahertz is probably better to call it an antenna, and above 1 gigahertz, it's a feed horn for the microwaves. But before I run down there, I do an RFI check. So I do a quick RFI check with an AirSpy SDR, looking around. And in this case, I went right up the middle of the ham band. So between 415 and 435 is the middle of the UHF ham band. It's the quietest radio spot out there. So I did this 10-minute collect. And again, you can see the signal in there. It's a broadband signal. If it was narrowband, you'd just see a black dot. You wouldn't see the black lines going across all the frequencies. The 3 plots on the right are the period derivative, and then a 2-dimensional view of that. You want the peak signal to noise ratio to occur at the correct period. In this case, the period is 714 milliseconds, and they have very strong peaks there. And then the final one is the little plot in the middle of the bottom with that sharp peak. And it says the peak signal to noise ratio is at the dispersion measure of 26. So the dispersion measure of 26 is the published value. And we have a very sharp peak there, which all of this all indicates a very good pulsar. If your peak SNR occurred on the axis, say your peak SNR occurred at 0, that means there's no distance between you and the supposed pulsar, which means you got RFI right in your shack that you're finding and not a remote pulsar. So all of these things contribute to a conclusion that, yeah, this is a good pulsar. Next one. And we can do further analysis of it. So again, this was 10 minutes, 30 megahertz bandwidth last August. And the Presto plot, so I've got it all scripted now, so it runs automatically. So when we're done collecting the data with the B210, it automatically goes to the database, gets the ephemeris values, computes everything, and runs Presto automatically, and I get that plot. Now, if the plot turns out to be poor, you can always fine tune it by hand, but that one came out real nice. And then on the right, I'm showing the dynamic spectrum. So the dynamic spectrum is also just called the waterfall. And you notice there's some ripple in it, and that's fine for what we're doing. We actually operate just below saturation because these pulsars are so weak. And we can even operate at saturation. So we turn the gain up and we tolerate, and that's just normal passband ripple that you're seeing there. We've measured that. But we exaggerate it to get up near saturation so we can even find these pulsars. And then at the bottom, it just says flat time series. So that's just a time series plot. And it's nice and flat. That's what we want to see. Next one. So this was a complete failure. This one was 3 hours of data we collected. Again, the frequency plot shows it was at 400, but there's no indication whatsoever on the Presto plot that this is a pulsar. Nothing converges. It looks terrible. And if you look on the left, that's the time series plot, and that's horrible. And if you look at that, you realize there's some major noise problems. There's both RFI and red noise. Red noise is low frequency harmonic noise, like 410 hertz, something like that. So low frequency harmonic noise, it just destroys your signal to noise ratio when you're looking for a pulsar at 1 second or something at the same frequency. And if you look at over on the Presto plot, if you look at the phase time plot on the left there, at the bottom, you see a whole bunch of junk, and then in the middle, and then again on the top, that's some RFI. So we try to keep things quiet at Haswell. Some of the RFI comes from our own trailer. There's some solar panels on top. The solar panels are noisy. We try to turn everything off. We turn off, if it's the wintertime, we turn off the heater, try to turn off the air conditioner, turn off everything when we're running. But you can still get external RFI, and sometimes you can't figure out what it was. So this is just what a bad one looks like. Then next chart. We'll just quickly show a couple of good plots here. Again, Presto, there is a learning curve on it, but this is what the amateurs are using, and it does run on Linux, but it's a very good, well-supported package. I guess in the middle on the frequency phase plot, again, you see some strong ripple in there. That's just showing that, yeah, we're operating near saturation on the SDR, but we still get a real good response on the Pulsar because we collected data for 30 minutes. And the period on this is 500 milliseconds, so half a second. So we have thousands of folds there. So we collect up all that data and fold it, and that's why the Pulsar can come out. Next one. So way back at the beginning, early on, I showed at the very top here, I showed that time series of what a typical pulsar looks like to us in just the raw time series. Now we can go in and analyze it with our software, B0835-41. On the left is Presto. It doesn't look too bad. We get a lot of them that are like this. You look on the left, the far left of the phase time plot. You can see that there's signal there. It's not real strong, but you can certainly see it. On the very top, the two pulses look good. They're standing out way above the noise. The signal to noise ratio is increasing throughout, and period look good. And so I computed the signal noise ratio here on Presto as 12.7, which is not bad. Then over on the right, I run the totally independent time series algorithm. The time series algorithm does better on slower pulsars. So Presto does better on fast pulsars, say pulsars running at 5, 10, 30, even 100 milliseconds. The time series does better on slower ones. So this one is 3/4 of a second, a relatively slow one. And it gives a different plot. So it's 1.5 phases of the plot, but you see 2 instances of the very strong signal sticking up there, exact same period, which confirms the pulsar, and it had a much stronger signal noise ratio, but I subscripted the signal noise ratio because a time series SNR is not the same as a FFT SNR. They're you can correlate them. They both trend up and down, but they're not the same measure. So the time SNR will generally be higher. Let's go to the next one. This one is interesting. On the left, it's a fairly poor Presto plot, but the period, you have a peak SNR at the right period, 343 milliseconds. And if you look at the frequency plot, you can you can kind of see the phase in there, and the same thing on the time phase plot. You can see it, and the two best pulses look like there's they're up above the noise floor, and it's got a little weird notch in the pulse. But if I go over and run the time series algorithm on the right, again, the pulse looks like it has that strange notch. Well, indeed, it's called a mode changing pulsar. A mode changing pulsar has two peaks, and they have there's one strong peak, and then there's a smaller peak, and the smaller peak switches back and forth. It kind of rotates around the stronger one. So it's mode changing. You never know for sure where that second peak is going to be, but it moves around. The other interesting thing here is the on the time plot, especially on the right, you don't see much. If you look at the phase plot, you don't see hardly any. Oh, I forgot to mention on the time series plots, time runs down. Time starts at the top and runs down to the bottom. So it's the reverse on Presto. But when you look at the time plot, the pulse only shows up like around 9,000 seconds late. It's so that you only have a signal the very last portion of the collection. And the same thing on the left. If you look over on the far left at the pulse, at the phase time plot, again, you only see pulse at the very top, at the end of the collection. When I first got this, I thought, oh, something's wrong with our equipment most of the time. But I showed this to the guy in Germany. He says, oh, no, we get the same thing all the time. This one's frustrating. It's because of the scintillation. So this one has very strong scintillation, which is caused by the hydrogen clouds that rapidly move around and distort everything. And then you get a window of time, and you get a strong pulse. So in this case, on Presto, the SNR in the frequency domain was 4.8, which is getting pretty low. We can go down around 3.5 on Presto, but the signal noise ratio on the time was 16.3, which is still doing pretty good. So I tend to use both algorithms to actually confirm that we have a pulsar and make a claim. Then I've got one more chart. Just go to the next one. This will be the last one. I just wanted to mention a research area. So it's called the timing residuals. When you compute the time of arrival of the pulse and you have a model of the pulsar, so what you end up doing is comparing the modeled or the predicted time with your observed time of arrival. And there's always a difference. There's these slight residuals that are down in the millisecond range. And so they'll develop a model of the pulsar, of its companion. It's in orbit. You have the orbital dynamics. You have to worry about Keplerian orbital dynamics, all the clouds of dust and gas between us, and all the various factors. You model all that, you still have a residual. And so this is where the nanograv group comes in. The nanograv stands for North American Nanohertz Observatory for Gravitational Waves. Nanohertz means that the wavelength is up in it's actually from months up to years, like dozens of years down to months is what they're looking for, these gravitational waves. And they do some high precision radio timing of these millisecond pulsars we're looking at. So Earth is in the middle on this plot, and scattered around in the sky, you have these millisecond pulsars, which are very stable. And let's imagine that there's a super massive black hole binary merger. That's what the SMBH is. So if there's a super massive black hole binary merger, theoretically, it would cause a stochastic gravitational wave background. Stochastic means a statistical gravitational wave background in the nanohertz range, which means the frequency, the wavelength is up on the order of years. And it would affect each and every pulsar in the Milky Way. And there would be very slight differences in the timing of the arrival of the pulsar, of the pulses, but those could be detected by the clocks here on Earth. And so this nanograv group has been doing this. They're using, or they used Arecibo until it broke. They use Green Bank and some other radio telescopes and collect data constantly. They've been doing it for 15 years. They have not yet been able to make claim that they've detected a gravitational wave in the radio region, simply because they've been doing it 15 years. Let's say it's a 30-year wavelength. They only have half a wave so far. It's just incredible what they're doing, but they're getting closer. They have a lot of confidence in what they're doing, that in the next several years, they'll be able to declare that, yeah, they've detected gravitational waves through radio. Meanwhile, there's other science. They can determine the mass of these neutron stars from these residuals. They do the studies of the hydrogen. They study why these profiles of the pulse vary so much. They've done very extreme tests of general relativity. So there's, if you go to that website, nanograv.org, you can download their data and their code and get involved. There's a lot of, there's student projects, a lot of things to do with that. So that's my last slide. Let's see if there's time for any questions.
All right, well, you give them a hand if you can hear it on Zoom. Yeah, anyone have questions on the presentation?
Yeah. I was wondering, how is the dish mounted and controlled? Is it like azimuth elevation or equatorial?
So it is ASL.
Okay, and do you have issues with ASL precision, or you just have enough resolution that that you don't have issues with that?
So yeah, that's the three software guys that did it. They've spent several years developing the software to do all that, and they have the encoders in place and the Raspberry Pi controller. So they've worked through all that. There were issues at first, but I just got involved a couple of years ago. They did all the hard work, and I get to come and have fun.
Nice. Yeah, I know you could get around quite a bit of that with an equatorial mount. It, you know, just cancels out the rotation of Earth's Earth's rotation, but it's not as easy to steer, right?
Yeah, but if you're out there, like if we're tracking a pulsar, because we're not going at the Earth's rate, you'll hear the motors kick in several times a minute. So it'll kick in and just run for a couple of seconds and then turn off. So the motors constantly turn off and on to keep us on target.
Okay, that's cool. Thank you.
Yeah.
And then, so I had one other question. What kind of receive amplification do you guys use?
You mean like the LNA?
Yeah, you said you crank the LNAs basically to the max of what you can, and you're seeing like you're running them right at saturation, right? And you're seeing ripples from those. Is that from the LNA, from your SDR, or both? Or
well, the passband ripple comes from the LNA. The LNAs, so Ray Uberek and AA0L, he does all of our RF engineering, and he gets them from that place in Texas. There's a microwave place in Texas that sells these LNAs. They're not very expensive, but and we just operate at ambient temperature. We don't have anything cooled. So the LNA, inherent to any passband there, you're going to have some passband ripple. So I'm sorry, right after the LNA, we have a filter. The filter is causing some of that, the passband ripple that you see in the SDR picture. The reason why you see it, instead of seeing a nice flat response, the reason you see it is we've got the gain on the SDR turned up so high. We operate the SDR almost where it's saturated on, just solid yellow color. We back off a little bit, but we have operated very high gain on the SDR. So I think that exaggerates the normal ripple that you'd see.
Okay, that makes sense. Interesting. So you just have one LNA stage before your SDR, or you
just one. And depending on the feed horn, each one has its own, but there's just one LNA up there. So, and normally we operate receive only, as a radio telescope, receive only for pulsars or anything. If we're doing the Earth moon bounce, then what Ray does, he brings his 200-watt transmitter from home, and we go up and install that up at the feed horn. So we don't leave it there for long time because the transmitter is not going to survive the weather, but it's we'll put the transmitter up there, 200-watt transmitter, because if we're doing a moon bounce contest, we have to be able to transmit and receive. So with the 200-watt transmitter up there on that 60-foot dish, we have a huge effective radiated power.
That's cool. Yeah, you need quite a bit of power to do EME. Is that like a software-defined transmitter? I'm assuming if you're putting it up in the feed, or
no, it's an analog one that he puts up.
Interesting.
Yeah.
That's cool.
Yeah, it's a lot of fun. Like I said, we welcome students. We have some other student members doing projects, and you don't have to live in Colorado because a lot of things we can do remotely. We can't control the dish remotely. We have a 2-person rule in effect on the dish, the 60-foot dish. So 2 people have to be there whenever we're operating it, simply because if something went wrong, we drive that dish into the ground, we're done. That's the only one we have. But the other projects like Radio Jupiter, so Radio Jupiter we have on TeamViewer, we can access that from home, or the interferometer, we'll be able to access that from home, things like that.
I have more questions. All right, well, I think that does it for us. Yeah, I'll stop the recording here. Thanks so much for the presentation. That was
sure. Yeah.
fantastic.
Yeah. Glad you guys are